It was a cold morning in December 1943. A mighty ship, the pride and last hope of her fleet, the battlecruiser Scharnhorst, sailed through the leading waters of the North Sea, accompanied by several destroyers. Her crew did not know that this would be the ship's last battle, after which only a few would survive. But before that, she would put up a stubborn resistance to the enemy, who had organized a hunt for her, comparable only to the famous hunt for Bismarck. But let's go back in time to find out what kind of ship she was, what she did during the war, and how she ended up trapped in the North Sea. In this first part, we're gonna talk about Scharnhorst's birth, what kind of problems faced engineers during her production and how they solved them, and what kind of ship she ended up being. Our tale begins in 1920. After the defeat in Great War, Germany was devastated, and its fleet utterly destroyed. The remnants of Kriegsmarine faced interwar period with great struggle. Red revolts, revolutions and fightings for a spot in the sun became the new reality. The naval commanders were changing one after another before the position took Erich Raeder. This man was behind the revival of military might of German fleet. German naval staff wanted to replace some of old pre-dreadnought ships, which became the main naval forces after the war, and it sparked intense discussion in the Reichstag of the young Weimar Republic of the best way to use a tonnage allowed by the Treaty of Versailles. There were severe disputes between different political fractions. Many were not enthusiastic about returning to naval power of Tirpitz period and wanted to hear nothing even about limited shipbuilding programs. After spending a couple of years negotiating, fleet was finally allowed to start a shipbuilding program strictly kept to Versailles restrictions. According to the design, it was a diesel-powered ships with, as Germany tried to assure others, a standard displacement of 10,000 tons, lead ship Deutschland. 7.6 283mm guns in tow turrets with 8 150mm guns and 26 knot speed, they were powerful enough to counter any cruiser except battle cruisers and fast enough to get away from any battleship of a time. This project impressed maritime parties, who quickly nicknamed them pocket battleships. But the reports, which appeared after the laying of third ship, telling about the new French project with higher speed and powerful armament consisting of 8 330mm guns, future Dunkirk, instantly made pocket battleships obsolete. First reaction of Admiral Raeder was to try to expand the displacement of 4th and 5th ships to 15 or 18,000 tons and add them as third turret. In November of 1932, Raeder and the Minister of Defense came to an agreement on the future composition of the fleet. In 3 stages, by 1938, the fleet was to be completely renewed, receiving 6 battleships, 6 cruisers, 1/2 flotilla of destroyers and 1/2 flotilla of torpedo boats of 6-ship composition, 3/2 flotillas of torpedo boats, and if a change in the political situation occurred, 16 submarines. But the main problem that urgently needed to be solved was what the next battleships should be. In 1933, the scope of German naval planning was limited to protecting the coast and shipping in the Baltic Sea from the Polish fleet, which could be supported by the French fleet, protecting its own trade routes and operating on the trade routes of France. The Soviet fleet was too weak to take place in German plans, although the rumors were circulating of its large shipbuilding program. At a conference in Berlin on March 8, 1933, it was decided that the new ships should counter Dunkirk. The first calculations showed the need for a 320mm armor build that could withstand hits from 330mm armor-piercing shells from a distance of over 18 kilometers, and a thick armor deck that was supposed to stop these shells fired from over 25 kilometers. Such protection did not fit into the tolerable displacement limits, so the requirements were lowered. The ship should withstand hits from 330mm high explosive and 2 or 3mm armor-piercing shells. This could be achieved with a 220mm belt and 80mm deck armor. Considering the increasing danger of air attacks, it was desired to also armor the upper deck up to at least 50mm. The discussions on the main caliber mainly boiled down to finding a compromise between better armor penetration and destructive effect on one hand, and rate of fire on other. It was then decided that 9 283mm guns were better than 6 330. The turrets themselves could not be forgotten either. Only 283mm triple gun turrets were available, and all the other still had to be designed, tested, and put into production. A year was needed to develop a new main caliber mount, and another 3.5 years for the rest. In total, 3 basic designs were considered: 18,000 tons, 22,000 tons, both with 283mm guns, and 26,000 tons with 330mm guns. The most radical admirals, such as the Chief of Naval Artillery Gross, spoke out passionately in favor of a 26,000-ton project with 330mm guns, emphasizing that parity with France was most important. However, this project led to new problems. In the end, Raeder ordered a more detailed study of the 26,000-ton project. As a last result, it was permitted to use a 305mm caliber. The work was to be completed by the end of 1934, and the lead ship was planned to be laid down at that time. When Adolf Hitler came to power in Germany in 1933, he made it clear to Admiral Raeder that he did not intend, like Admiral von Tirpitz, to base his naval policy on a direct challenge to British naval power, but considered it more important to counter the French shipbuilding programs. He authorized the construction of the 4th and 5th armored ships of the Deutschland class, designated as D and E, but with increased protection, while maintaining the displacement limits of 19,000 tons and an armament of 2 triple 283mm turrets. At a conference in June, such a design with a 220mm belt, 70 to 80mm main and 35 to 50mm upper armor deck was the subject of detailed discussion. In particular, it was proposed to increase the main battery ammunition to 150 or 160 shells per gun, to place the secondary 150mm battery in 4 twin turrets for better ammunition supply and crew protection, and to strengthen the heavy anti-aircraft battery from 388mm barrels on the Deutschland to 4 or to 3 twin turrets with an increase of ammunition to 200 rounds per barrel. The torpedo tubes were retained. The new ships would be 5 meters longer than Deutschland, and their draft would increase to 7 or 8 meters. One of them was to be equipped as the fleet flagship, and the question of choosing the propulsion plant remained open, since the tests of Deutschland had already shown the shortcomings of diesel engines, noise and vibration. In the autumn of 1933, discussions on the project continued. Now, the placement of the 150mm guns in the turrets was criticized, the barbets of which did not reach the main armor deck, which made the turrets very vulnerable. Moreover, with a successful hit, 2 guns would be disabled at once. The development of the project for such turrets was completed, and they could be ordered as early as January 1934. It was desired to strengthen the anti-aircraft armament to 4 or 5 twin guns with 4 directors, located as on the cruiser Nuremberg. However, the expediency of having torpedo tubes was now questioned. The protection was strengthened by increasing the armor of the main battery turret barbets to 220mm, but the propulsion system and, consequently, the cruising range had not yet been determined. A week after this meeting, on October 18, it was decided to issue orders for two 19,000-ton battleships, officially presenting them as 10,000-ton successors to the Deutschland. Later in the minutes of the meeting, the figure 19,000 was crossed out and hand-corrected to 17,000, apparently to be closer to the Versailles limits. The armament consisted of 6 283mm guns in two triple turrets, 8 150mm and 8 88mm guns in 4 twin turrets for each type. In December, they returned to the issue of the main caliber. The budget included 1.4 million marks for the development of a new 330mm gun. But then, in an attempt to win the favor of the British, Raeder again decided to return to a 305mm caliber. A month later, such a long wait for the main caliber armament, until about May 1939, was considered unreasonable, and on January 25, 1934, the naval shipyard in Wilhelmshaven and the Deutsche Werke Company in Kiel received orders for the construction of the now 18,000-ton armored ships D and E, which were laid down on February 14 under construction numbers 135 and 235. In 1934, France announced the laying of a second Duncan-class battlecruiser, Strasbourg, and urgent actions was needed. Hitler gave the go-ahead to add a third turret and increase the displacement to 26,000 tons. Construction of the ships ceased on July 5, and the engineers began a redesign that, by the most optimistic estimates, could not be completed before October 1935. The new requirements included a 28 knots continuous speed and 30 knots total speed, citadel protection from 330mm guns at ranges of 15 to 20 kilometers, splinter protection of the ends, 3 main battery turrets, 1 in the bow and 2 in the stern, 4 twin guns, 150mm guns, and no torpedo tubes. At that time, for the first time, a proposal was made to provide in the project the possibility of replacing the triple-gun 283mm turrets with the twin 330mm or 380mm caliber turrets after completion. Soon, the defensive arrangement of the main battery turrets was abandoned, preferring a more familiar scheme with 2 turrets in the bow. As for the engines, sympathies were inclined in favor of turbines and high-temperature boilers, since only such a powerful plant could provide a speed of 30 knots. And thus, the design concept for Scharnhorst and Gneisenau was born. The new ships were not successors to the excellent German battlecruisers of Great War, but were simply enlarged armored ships of the 1920s, born of the restrictions of the Versailles Treaty. Even the composition of the medium-caliber battery was dictated by the guns already manufactured for the 4th and 5th ships of the Deutschland class. There were 8 single-gun 150mm deck mounts with shields, 4 per ship, which were not the most successful addition to the armored twin-gun turrets, the number of which had to be limited because of this, also for each. The ship received powerful armor protection, but without the upper citadel traditional for German battlecruisers and battleships of World War I. It was envisaged to use not only ready-made 150mm guns, but also some of the equipment intended for the 4th and 5th armored ships. Although the Germans often called Scharnhorst and Gneisenau battleships, they were in fact battlecruisers with powerful protection, high speed, and moderate, by the standards of that time, caliber of the main guns. The design of these, in fact transitional ships, became a development of the armored ship Deutschland and bore traces of technical limitations and political considerations, although during the redesign, Germans naturally used their experience in creating large, fast and powerfully protected battlecruiser of the First World War. Before the construction began, Hitler wanted to reassure Britain. Wanting to have a sufficient number of such ships to counter the French fleet, he decided to conclude a naval agreement with the Mistress of the Seas, giving the latter a guaranteed triple superiority in battleships over the German fleet, 474,000 tons against 166,000 tons. This allowed the Versailles restrictions to be legally removed. The Anglo-German Naval Treaty, which allowed Hitler to begin building a modern fleet, was signed in London on June 18, 1935, when both new battleships had already been laid down. The treaty guaranteed that German policy at sea would not be directed against Great Britain, but bound Germany by the obligation to comply with all existing international maritime agreements and those that might be concluded in the future. A new discussion on the main caliber began in March 1935, when the blueprints and specifications were almost ready. 5 options were considered: 9 305 or 330 mm guns, or 6 380, 350 or 330 mm guns, with the first 3 requiring a displacement of 34 to 37,000 tons, an additional 18 months delay, and an increase in cost to 30 or 40 million marks. The Navy preferred 350 or 380 mm guns in 3 twin turrets, despite the loss of 11 million marks already invested in the production of 283 mm guns and turrets. But Hitler objected to increasing the main caliber because of the potential for significant political complications with Britain. It was decided to use the 350 mm caliber on the next ship, called F. Since Scharnhorst and Gneisenau were built to counter the French Dunkirk-class ships, the offensive and defensive elements were comparing against the Dunkirks. The new 283 mm Krupp guns, superior to similar guns on the Deutschland-class ships, had enormous power and range for their caliber. The problem the German designers faced when designing the armor protection of the new ships becomes clearer if we compare the sizes of the French and German armor-piercing shells. The first, 330 mm, weighed 572 kilograms, and the second only 330 kilograms. But the 283 mm caliber ensured a high rate of fire and could penetrate the belt of the French from a distance of up to 20.5 kilometers. In addition, Dunkirk's hull had no armor at all over a large area, so the destruction of equipment in these parts would quickly make the ship incapable of combat. But the main reason for retaining 283 mm guns on the new ships was still political. During preliminary studies, it became clear that 9 283 mm guns and protection against 330 mm shells at limited visibility distances in the North Sea fit well into the 26,000-ton displacement. However, in 1936, weight control of materials at the shipyard during construction showed that the displacement would be much greater. This caused serious concern for the stability, seaworthiness, and survivability of the ships, since the armor deck, which according to the design was above the waterline, was now lower. The height of the freeboard was also reduced, which lowered the stability. Later, during the first voyages, it became clear that the increased draft made the ships very wet in the open sea, which is why it was necessary to urgently redesign the ship of the stern, the bow frames, and raise the upper deck in the bow. The shipbuilding department began working on the problem of increased displacement. The main characteristics of the project were no longer subject to change, so the only possible solution was to increase the width of the hull. But it was too late to rebuild the hull. The installation of the side blisters was also undesirable. The ships would lose speed and become even heavier. Any further changes to the project had to be carefully calculated. As a result, it was decided to increase the standard displacement to 31,500 tons. Work on the project was completed in May 1935, just by the time the tests of the new 283 mm guns were successfully completed. The most controversial element of the project was the power plant. At the initial design stage, turbogear units using high pressure and high temperature steam were adapted to speed up delivery times and guarantee high speed and power, since there were no suitable diesel engines for such large ships with a speed of 30 knots. Admiral Raeder took a risk by approving the composition of the power plant from steam turbines and high-temperature, high-pressure boilers. The new plant was tested only at the shipyard with the participation of future mechanics of the new ships. Everyone understood that the range would be much less than with diesel engines. But there was simply no time to wait for the development and manufacture of powerful diesel engines. These were the first capital ships in the world to be built with truly extensive use of welding. The hulls of Scharnhorst and Gneisenau were made entirely welded, with the exception of the places where the torpedo bulkhead were connected to the slopes of the lower armor deck. The quality of the welds was not always high, as was demonstrated by the damage to Gneisenau in June 1940. During the construction of these ships, the welding technology depended entirely on the length of the electrodes, which did not always allow for a continuous weld. When torpedoes and bombs hit, the welded areas of the bulkheads were destroyed, which was explained by the use of poor electrodes and sometimes by the poor quality of the work. Nevertheless, German shipbuilders unanimously considered welded hulls to be better than riveted ones. Gneisenau and Scharnhorst had bow bulbs to reduce wave resistance at high speed, which was further facilitated by the neat contrast and length of the hull. These ships were very different from their predecessors from the First World War and foreign contemporaries. Speed was considered the main thing for them, so they did not have side bulges, which would increase displacement and resistance to movement. The most noticeable feature of the hull of these ships after completion was the almost vertical stern and the small flare of the bow frames. The anchors were stored traditionally in hose holes, two on the port side and one on the starboard. The height of the freeboard, already small compared to foreign contemporaries, was further reduced during the completion process, when various equipment was added to the ship and the weight of some devices and systems turned out to be greater than expected. The situation was worsened by the 0.8 meter trim by the bow at full load, which could only be eliminated by using fuel from the bow tanks during the first 24 hours of sailing. These first 24 hours, when the waves rolled over the forecastle, creating problems with the operation of the Anton turret and interfering with the correct control of the ship, remained the most unpleasant downside during all the operations. Under certain conditions in the open sea, the lack of freeboard, the shape of the bow, and the location of the anchors led to the formation of such spray that the ship could only be controlled from the conning tower. Sea trials of Gneisenau at high speed also showed that with a straight stern, a huge bow wave was formed, which the ship pushed in front of itself. A similar phenomenon was also observed on pocket battleships. During a major overhaul in the summer of 1939, Scharnhorst received a new, so-called Atlantic bow with a large forward inclination of the stern, increased flare of the frames, and anchors moved to the edge of the deck. The length of the ship increased by about 5 meters, and the location of the anchors became the main distinguishing feature of Scharnhorst from her sister ship. The underwater hull shape was quite unusual. Instead of a smooth transition of the side to a flat or keeled bottom, the latter in the middle part had a horizontal plane ending with edges at the transition to the side. Such a bottom significantly simplified the construction, and in case of damage, it accelerated docking and repair. There was also a manual steering drive from steering wheels. 2 posts were located in the conning tower and on the navigation bridge, and the backup ones were in the command center of the twin deck, in each tiller compartment, and in the emergency steering compartment. Traditionally, German large ships had powerful armor, excellent division in the compartments, and good and tight torpedo protection. With the increase in the effectiveness of long-range shooting and bombing, Germans had to pay serious attention to horizontal protection. Already in 1934, they recognized the insufficient thickness of the armor decks of the Great War ships and developed the principle that neither horizontal nor vertical armor alone could withstand heavy shells. They also understood that heavy guns won the argument with armor and that absolute protection does not exist. Therefore, German designers decided to distribute the armor in such a way that at critical distances, horizontal and vertical armor helped each other withstand hits to vital parts of the ship. A shell that penetrated the side armor had to meet the armored deck on its way. Although this increased the risk of being blown up by a long-range shell or a bomb dropped from a high altitude, Germans believed that their ships would be fighting in the North Sea, where visibility conditions limited combat ranges. The Germans' armor protection system was not based on the zone of invulnerability concept adopted by other navies. Instead, they developed complex tables in range to target angle coordinates for the guns of the most likely adversaries among the British and French ships, on the basis of which the commanders of the German battleships and cruisers could choose the least risky combat distances. These tables, of course, did not guarantee complete safety, since much of the data in them was based on unreliable and sometimes erroneous information. Nevertheless, they were quite useful for developing common tactical decisions. The Germans did not consider the problem of diving shells falling slightly short of the target to be as serious as the Japanese, Americans and British believed. And yet, it must be recognized that with the increase of the effectiveness of long-range shooting, the German armor protection system turned out to be weak against most of the guns of the new battleships. The total weight of the armor was 14.2 thousand tons. The main vertical belt, 4.5 meters high and weighing 3.4 thousand tons, was 350 mm thick, tapering to 170 mm at the lower edge, 1 meter above which the main armor deck slope was attached. The belt thinned out, starting at a depth of 1.7 meter below the design waterline. This design was the same as on the Bismarck-class battleships, providing protection, belt plus slope, from 1,000 kg of 4 or 6 mm shells from distances over 11 kilometers. The Germans denied the use of a main belt inclined and offset inward from the plating for battleships, considering it unreasonable to leave the outer part of the side unprotected. The thickness of the main belt was constant along the entire length of the armored citadel from the slope to a height of 3 meters above the design waterline, where the 45 mm splinter belt began and reached the upper deck. Such a thin upper belt had to be used due to the great height of the main belt, chosen so that the side of the area of the waterline remained covered with thick armor during rolling, heeling, or increased draft after receiving damage. In front of the fore-end armored athwartship bulkhead, located 41 meters from the stern, the main belt thinned from 350 to 70 mm, having a significant height above and below the design waterline to provide splinter protection for the fore-end. The steering gear and shafts were protected by 80 mm armored slopes and a 37 meters long, 70 mm thick splinter belt running from the stern traverse bulkhead of the citadel to the stern bulkhead of the steering gear compartment. The Germans considered it essential to provide protection for the propellers and rudders from projectiles and bombs, although they understood that it would not be completely reliable, especially from torpedoes. Ships of this type had armored traverse bulkheads at the ends of a citadel and another one protecting the steering gear compartment from the stern. The fore-end bulkhead ran from the upper platform deck to the upper deck. Under the armored deck, its thickness was the same as that of the steering gear compartment bulkhead, and above it 150 mm to the battery deck and 70 mm from the battery to the upper deck. The Germans used the so-called carapace armor deck, weighed 3.2 thousand tons, which was attached to the lower edge of the main belt with bevels and did not lie on top of it, as for example on Yamato. The German designers believed that if the main armor deck was placed at the level of the upper edge of the belt, shells and bombs that hit the ship would explode too high in the hull. In addition, any protection behind the belt, which could be penetrated by shells, disappeared. Against general-purpose aerial bombs, they also used an upper armor deck 50 mm thick, weighed 2.1 thousand tons, which was also supposed to arm the fuse of the armor-piercing bombs, causing them to explode above the main armor deck, located 2 inner deck spaces below. When a semi-armor-piercing shell capable of penetrating a 50 mm deck and exploding hit a ship, the fragmentation damage was limited by the system of longitudinal and transverse bulkheads running between the upper and lower armor decks. It was assumed that the heavy armor-piercing bombs could penetrate both decks, but it had to be dropped from a great height with an insignificant probability of hitting. Since it was not possible to conduct tests with armor-piercing bombs dropped from a high altitude, they were replaced by field tests of vertical armor, which was fired at with heavy shells, simulating the effect of an armor-piercing bomb. The results showed that horizontal protection from one thick deck was impractical. The design of the deck protection should be such as to reduce the kinetic energy of the bomb, deform its body in fuse. Therefore, they settled on using 2 armor decks with the greatest armor thickness closer to the side of the lower one, that is, on its slopes. The upper armor deck was 5.1 meters from the lower one, and between them there was a battery deck with a regular steel flooring. The design of the lower armor deck was almost identical to that of the First World War battlecruisers of the Ersatz-York type, where the single armor deck extended most of its width just above the waterline, and its slope descended to the lower edge of the main belt at an angle of 25 degrees to the horizontal. This arrangement, one deck lower than on most battleships and battlecruisers of the time, provided better protection for the vital parts of the ship. Apart from hits from diving shells, these ships were well protected from the artillery fire of battleships of that time at distances when the belt and slope of the deck stood in the path of the shell. But at very large distances, the deck was already penetrable. With a displacement of over 26,000 tons, it was impossible to use a single armor deck located at a level higher than the lower one, since this required raising the belt. Moreover, when designing Scharnhorst, the emphasis was on resisting shells, not bombs. Here, the Germans showed themselves to be very conservative, retaining the principle of armor as in the project of the Great War. In fact, until May 29, 1937, when the armored ship Deutschland received 2 bomb hits in the Spanish harbor of Ibiza, they did not take the danger of attacks from the air seriously. These 2 bombs caused severe damage inside the hull, killed 31 people and wounded many more. Later, the results of the bomb hits on Scharnhorst in July 1941, when it was moored in La Palisse, caused great concern in the shipbuilding department. After all, some of the bombs penetrated both armor decks and did not explode only by a lucky chance. A special commission was sent to France to raise these bombs for testing. Unfortunately, the draft and displacement restriction did not allow for any strengthening of the deck armor on Scharnhorst and Gneisenau. The main armor deck was not on one level. Over the 9.6 meters above the boiler rooms, it had to be raised by 60 centimeters to provide sufficient clearance over the tops of the boilers, which turned out to be larger than originally planned. According to the design, the main armor deck was 53 centimeters above the waterline, but changes in the armor and other modifications increased the displacement and draft. As a result, the deck was level with the waterline, and at full load even sunk 73 centimeters below it. The situation was not easy to fix. The only solution was to add bulges or increase the width of the hull. But nothing could be done until serious damage to the bow Gneisenau led to a modernization, during which it was planned to lengthen the hull by 10 meters. The Germans preferred to armor the main and auxiliary conning towers well. These ships were no exception. An armored 200 mm communication pipe ran from the lower armor deck to the floor of the main conning tower, 350 mm walls, 200 mm roof. The stern conning tower had slightly thinner armor. The main caliber fire control post was protected by 60 mm armor plates and auxiliary devices by 20 mm plates. The rear walls of the turrets were unusually thick, 350 mm, for better balancing. The side walls, 180 to 220 mm. Different sources give different figures. The front part, 360 mm, and the roof, up to 180 mm. The thickness of the barbets varied from 350 to 200 mm. In general, the main caliber artillery turned out to be the most protected part of these ships. 2.7 thousand tons of armor went to it. The protection of the medium artillery turned out to be weak. And while the turrets of the 150 mm guns had armor that was thicker than on most allied battleships, but still unable to withstand direct hits from heavy shells, the deck mounts were protected only by 25 mm shields. Scharnhorst and Gneisenau had extensive splinter protection above the main armor deck, as was common to all German heavy ships. Most of the bulkheads were located within the citadel to limit damage from shell and bomb explosion on the main armor deck. The funnels were protected by 20 mm plates, as were the main caliber fire control post and the night fire control post. The underwater protection was designed to withstand the contact explosion of a 250 kg charge of TNT at a depth of half the designed draft. This charge was slightly smaller than that of the torpedoes of the British Navy, but was superior to the charges of the British air torpedoes. The design of the torpedo protection was developed on the basis of full-scale tests with various sections cut from the hull of the old battleship Preußen. The tests showed that welded joints, although lighter than traditional riveted ones, withstood the explosion of a 250 kg charge better, and the damage caused by this was easier to repair. Even earlier, a welded joints of armor plates that had not been heat-hardened was tested by shelling at an artillery range, and the results were also positive. All this convinced the German designers that welded joints could withstand the stresses and bends that would occur during an underwater explosion in the anti-torpedo bulkhead, which was planned to be made from unhardened armor steel. Despite the results of these tests, which showed the ability of welded torpedo protection to withstand the explosion of a 250 kg charge, the Germans decided to fasten the anti-torpedo bulkhead with rivets, since it was impossible to fully guarantee the high quality of the welds. Defects in welded joints were detected only by X-ray, and the Germans had not yet mastered such tests at the shipyards. At the same time, they decided not to make any fastenings of cables and pipelines to the anti-torpedo bulkhead, since they would only reduce its elasticity, and they themselves could be destroyed during an explosion. The torpedo protection had light armor on the outer hull plating, the thickness of which varied between 12 and 16 mm under the main belt, and which could cause the torpedo warhead to detonate. However, there was the problem of damage to the inner bulkheads by fragments of the outer plating during the explosion of a very powerful charge. The large empty space behind the outer plating acted as an expansion chamber for the gases released during the explosion, which would significantly reduce their pressure and energy. Further inside the hull were oil tanks, which absorbed the remainder of the explosion energy by dissipating or destroying the 8 mm walls, reinforced with longitudinal stiffeners and frames. Part of the energy had to be absorbed by plastic and elastic deformations of the 45 mm anti-torpedo bulkhead, behind which, where possible, there were empty compartments along the citadel, absorbing possible leaks through it. The total thickness of the bulkheads along the citadel was 53 mm. In general, the torpedo protection repeated the protection of armored ships. Only the main belt was further from the center of the ship and went vertically. External bulges were abandoned in favor of a system of internal bulkheads. In the middle part of the hull, the anti-torpedo protection was quite effective, but toward the end of the citadel, where the hull narrowed, its resistance dropped to 200 kg of TNT, The hull structure in the area of the stern turret turned out to be very complex due to the sharp contours and the passage of the side propeller shafts through the anti-torpedo protection. The propeller shaft corridors were used as part of the underwater protection. Each time these ships received underwater damage, new shortcomings of their anti-torpedo protection were revealed. The anti-torpedo protection extended from the bottom almost to the upper edge of the armor deck slopes at an outward angle of about 10 degrees, where it was fastened with rivets. This part of the structure was already experiencing strong bending stresses under the hull's own weight, which were further increased by excessive overload. Even without additional impact loads, the shear stresses in the rivets could exceed the permissible limits. In fact, when a bomb or shell hit the slope of the armor deck, the attachment point of the underwater protection system was seriously tested, since the rivets in the area of the stern turret were always under high stress, mainly to the abrupt end of the traverse bulkhead and partly due to the end of the underwater protection system at about half the draft. From here, the bulkhead was deflected inward to have a greater distance from the plating, but the structural effectiveness of the underwater protection system was reduced. Due to the large dimensions of the main machinery, the anti-torpedo protection system turned out to be too narrow. Under such conditions, it was necessary to abandon the system used on the Superdreadnoughts Baden and Bayern, which was repeated on Bismarck and Tirpitz. The ships of the Scharnhorst class were designed for speed over 30 knots with a width limitation of 30 meters. But only with an increase in width and displacement could better torpedo protection be provided in the area of the main caliber turrets. As a result, the torpedo protection system on these ships turned out to be far from desirable. On these ships, the Germans applied the principle of ensuring a high degree of stability by means of excellent division of the hull into compartments, which had proven its reliability during the Great War. Due to the increased size of the ships, they were required to have even greater stability than on Deutschland. The Germans believed that the capital ship should be divided into many watertight compartments and that the principles of the International Convention for the Safety of Life at Sea, developed for passenger ships, should be applied to it. These ships were designed as two compartments, on which the flooding of any two adjacent compartments, regardless of their size and location, should not lead to the immersion of the deck to which the watertight bulkheads reached. Any main watertight compartment, with the exception of the narrowest ones at the ends, was divided into watertight spaces. The Jutland experience of the Lutzow and Seydlitz proved the absolute necessity of these principles for keeping the ship afloat. In the design of the new battlecruisers, the Germans also used the experience of the damage to the Bayern by a Russian mine in Great War. As a result, Scharnhorst and Gneisenau received many more longitudinal and transverse bulkheads than all previous German capital ships. The power plant was located in several large compartments to ensure separate power supply to each propeller shaft. The Germans deliberately went for the complexity of servicing the mechanism due to the difficult access to them. This primarily concerned the increase in the numbers of watertight hatches in the bulkheads and the use of watertight locks. As a result of careful analysis of stability characteristics at an early stage of design, the ships were divided into 21 main compartments by 6 beam bulkheads extending to the gun deck and 14 bulkheads extending forward to the upper deck. Anti-torpedo bulkheads had 15 side compartments on each side. These ships were designed to float if any 3 main compartments lost buoyancy. The arrangement of the transverse bulkheads was determined by calculation of the length of the flooding curves, using the methodology adopted for merchant ships. However, in a warship, the flooding of compartments usually is asymmetrical, so on large German warships, a greater hull width and a greater metacentric height were used to compensate for asymmetrical flooding. In this case, the resulting list and trim could be corrected by counter-flooding within a certain time. The estimated length of a hull from a torpedo hit was taken as 30 meters, or at least 3 compartments. Flooding from shell hits was considered less intense and could be more easily controlled. To account for differences in the ratio of weight loads to the center of gravity, separate combat stability calculations were made for each ship. Nevertheless, Scharnhorst and Gneisenau had mediocre stability characteristics for their size. Their relatively small range of stability, compared to ships of other fleets, was explained by the forced economy of armor weight and the reduction in silhouette, so that the enemy would have as small a target area as possible. The length-to-draft ratio of these battle cruisers was 16:1. The ships of Great War were built with even lower freeboard, but bearing in mind the transfer of combat operations of Scharnhorst and Gneisenau from the Baltic and North Sea to the Atlantic, they had to increase the height of the site. In addition, the increase in displacement and size required a significant increase in the rigidity of the hull. These ships could continue to fight even if the load-bearing elements of the framing were damaged. The Germans considered this very important, based on their experience in the battles of Great War. Therefore, they increased the thickness of the load-bearing elements of the framing in the upper part of the hull. Taking into account the protection requirements, this explains why these ships had a fairly high center of gravity. Width limitations prevented the corresponding increase in metacentric height that was achieved in subsequent projects. The Scharnhorst-class ships had a double bottom 1.7 meters deep. At the time the design work was completed, magnetic fuses for torpedoes and mines did not yet exist. The exit to the Atlantic and the return of the ships were supposed to be carried out in channels free of mine laying or under escort. The damage to Bayern in 1917 showed that only a deep double bottom could absorb the energy of an underwater explosion. The vital parts of the ship inside the armor citadel were separated from each other by two longitudinal bulkheads located 7.3 meters from the center line. These bulkheads, which the Germans began to use on pre-dreadnoughts, maintained the watertightness of the engine rooms and magazines, which significantly reduced the risk of a large leak in the event of a damage to the same site. A single bulkhead along the center line, although it reduced the amount of water entering the hull, increased the heeling moment to a greater extent than two bulkheads located at the sides. The Germans were convinced that a three-shaft power plant allowed the ship to be divided into compartments more effectively than a four-shaft one. The 283mm guns, with a barrel length of 54.47 calibers, were an improved version of the guns developed for the pocket battleships of the Deutschland class, and were placed in the same three-gun turrets: Bow, Anton and Bruno, Stern, Caesar. The latter made it possible to significantly reduce the construction time of the ships. Like most German mounts, the turrets had electric horizontal guidance drives, but all other movements were carried out using hydraulics. Although the weight of the rotating part of the turret was 750 tons, the horizontal speed turned out to be quite decent, 7.2 degrees per second. The design of the gun was typically German: an inner tube, or tube A, a replaceable liner replaced from the breech side, a two-piece casing mounted on the tube A at approximately 2/3 of its length, breech screwed into the rear part of the casing while hot. The breech was of the horizontal sliding type and provided a fairly high rate of fire for such heavy guns, a shot every 17 seconds. The excellent rate of fire was also facilitated by the high vertical aiming speed, reaching 8 degrees per second. The angle of maximum elevation of the barrels of plus 40 degrees was the same for all turrets, but the angle of depression was slightly different: -8 degrees for Anton and Caesar and -9 degrees for the elevated Bruno. The projectile for the new gun was longer, but carried less explosive than the projectile for the previous model. The main difference was that the extra weight in the new projectile went to the cap and aerodynamic tip, which provided better armor penetration. The Germans used three types of shells. Armor-piercing, used mainly against heavily armored targets, had a small explosive charge and a base fuse. Semi-armor-piercing of general purpose with the same base fuse, containing slightly more explosive filling and accordingly having a greater fragmentation effect. They were used against targets protected by not very thick armor, which they could penetrate. High explosive with a head fuse, which were used against unarmored targets such as destroyers, when a powerful fragmentation effect was required, against unprotected personnel, open anti-aircraft guns, fire control posts, searchlights, etc. The Germans followed these rules for using this or that type of shells throughout the war, although they all called them the same, Panzersprenggranaten. The last two types had less weight and an initial velocity of 900 meters per second, but the ballistic characteristics were approximately the same as armor-piercing, which simplified the control of fire. The shells were loaded using a hydraulic drive at a fixed elevation angle of the barrel of +2 degrees, which was also determined by the desire to fight at close range, i.e. at low elevation angles, and made it possible to reduce the time it took to move the guns after loading into the firing position. The propellant charge of propellant powder weighed 119 kilograms and consisted of two parts. The rear charge, 76.5 kilograms, was stored in a 47.5 kilograms brace case, and the forecharge, weighing 42.5 kilograms, was stored in a sealed cartridge case. At both ends of the rear charge and at the base of the forecharge were installed fuses made of 360 grams of coarse-grained black powder. The ballistic qualities of the 283mm German guns made them effective against the new French Dunker-class battlecruisers with 225 to 283mm belt and 310 to 340mm barbettes armor at normal combat ranges. Due to displacement limitations, a successful battle with the Dunker-class ship required an economical, from a weight standpoint, arrangement of the main caliber guns. They settled on the option with 3 triple-gun turrets, since such turrets for the 4th and 5th armored ships of the Deutschland class had already been designed and materials had been prepared for them. And this meant a lot in those conditions when the German metallurgy had to provide steel not only for the Navy, but also for the Army and the Air Force. All previous German battleships and battlecruisers carried their main guns in twin turrets for better fire control and equal distribution of fire to the bow and stern. In those cases, considerations of saving weight and materials were secondary. The systems for preparing and feeding ammunition to the turrets, 2 shell magazines under 4 loaded magazines, remain the same as on the armored ships, with minor modifications due to the increased weight of the shells. Shells were fed from the racks to the ring roller table using an overhead rail and grips, and from there to the hoist. The rear charges and brace cases were fed to the hoist using inclined sliding trays and traverse grips, and the forecharges were fed manually. The left gun hoist passed between it and the central gun, on the other side of which the other two hoists passed. In the hoist's loading carriage, the rear charge was located above the forecharge. The latter was loaded into the gun manually, and the rear charge was loaded using a hydraulic pusher, like the shell. Within the firing compartment, the shells and charges were moved using overhead drives. The ammunition consisted of 1,350 main charges, the same number of forecharges, and 450 shells of each of the 3 types mentioned. There is 150 per gun, an unusually large amount for the main caliber. During the design work, Hitler rejected Admiral Raeder's proposal to increase the caliber of the guns to 380mm. But after the signing of the Anglo-German naval agreement and the start of construction of the new French battleships of the Richelieu type with 380mm main caliber, the Führer gave the go-ahead for such a replacement. In his book Mein Kampf, he had strongly criticized the insufficient armament of some German ships of Great War, and now also felt that the armament of the new battlecruisers was weak. Therefore, for their subsequent rearmament, a contract was signed for the production of 380mm 52 caliber guns. The replacement of the armament was planned for the winter of 1940-41. But in 1935-36, the construction of the ships was already at such a stage that replacing the main caliber would have greatly delayed it, since work at the shipyard would have been suspended during the design and manufacture of new turrets. Although the triple-gun 283mm turrets were in many ways similar to the twin-gun 380mm turrets, there were also significant differences in the supply of ammunition and loading. It would have been necessary to move sub-traverse bulkheads and slightly alter the magazines. Therefore, it was decided to carry out rearmament as soon as special turrets for 380mm guns were ready. An important problem in this case was the increase in draft and trim by the bow, which were already causing concern. As a result, it was decided to increase the width of the hull and move the main armor belt outward. New blueprints of frames were already done, in which the attachment points of the plates remained unchanged. These plans were abandoned at the outbreak of war, but were later recalled when Gneisenau was heavily damaged in a raid on Kiel on February 26 of 1942. The choice of secondary battery was based on two factors. 8 150mm single gun mounts were available, and Rheinmetall Borsig had already developed a design for a new twin gun 150mm turret. Therefore, both ships received an unusual combination of 4 twin gun turrets and 4 single gun mounts. The intention to place all the secondary artillery in twin turrets remained unrealized due to weight considerations. The 150mm caliber had been standard for large German ships since the beginning of the century. The single gun mounts, located on the sides of the funnel close to each other, had 25mm anti-splinter shields and a mutual ammunition supply for each pair on one side. More reliable protection could not be provided due to the increase of weight and the reduced horizontal aiming speed. The usefulness of these mounts was questionable. In the last Battle of Scharnhorst, they were the first to fail. When they were used simultaneously with two-gun turrets, problems with fire control arose, mainly due to the different rates of fire. Thanks to better supply and power maintenance, the turret once fired slightly faster. The same difficulties arose when firing illumination shells at night. 4 twin-gun turrets, located on the edges of the single-gun mounts, provided the latter with additional cover from acute cross angles. The turrets had power-driven aiming drives, and their crews were protected by more powerful armor, and the supply of ammunition was better. Taking into account the armor and equipment, the weight of the rotating structure was about 126 tons. The main task of the 150mm guns was to repel attacks of cruisers and destroyers, for which a rate of fire of 6 to 8 rounds per minute was considered quite sufficient. The chief of the Artillery Bureau of the German Navy, Rear Admiral Karl Winzel, wrote about the choice of 150mm guns after the war. Quote, "We had an enemy with a large advantage in destroyers, and therefore needed medium-caliber artillery capable of quickly and effectively operating against large destroyers, as well as repelling massive attacks by smaller torpedo ships. Therefore, based on large-scale field tests and shelling of target ships, we came to the conclusion that a 150mm gun was necessary for very fast actions against patrol ships, as well as against transport convoys. However, due to its large weight and insufficient rate of fire, it was not suitable for actions against aircrafts. The American 127mm and British 133mm universal guns did not meet our requirement for a quick and decisive rebuff to destroyers." End of quote. The question of a universal gun was also considered, but in 1935 the Germans did not consider it possible to create a truly rapid-fire, mobile and powerful gun suitable for action against surface and air targets. German naval artillery experts believed that the secondary battery of a battleship should have a caliber of at least 150mm, and such a gun could not be made a good universal one due to the lack of time fuses and devices for their rapid installation. The speed of aiming the turrets was also selected for surface combat. The fuses were manually installed for each distance on the turret platform. The ammunition consisted of 1,600 charges in 8.75 cm long and 23.5 kg cases, 800 high-explosive 45 kg shells with a head fuse and a length of 6.5 or 6.8 cm, 845 kg semi-armor piercing shells with a bottom fuse, and 240 illumination shells. Not counting the illumination shells, there were 150 rounds per gun. 14 105mm general-purpose guns were located in twin mounts on the deck higher than the 150mm guns, with better dispersion across the superstructure and good firing angles. Some sources indicate that the guns were in mounts designed for 88mm anti-aircraft guns. With a rate of fire of 15 to 18 rounds per minute, an elevation angle of 80 degrees, and a muzzle velocity of 900 meters per second, the 105mm anti-aircraft guns provided effective protection from aircraft at close range, but were inferior to larger anti-aircraft guns at long range. The protection consisted of 15mm plates in the front, 10mm on the side, and 8mm on top and behind. The ammunition consisted of 6,020 unitary rounds. The projectile weighed 15.1 kilograms and had a 5.2 kilograms explosive charge. There were usually another 420 tracer rounds. The division of medium caliber into anti-ship and anti-aircraft proved quite effective for the European theater, since the British used relatively small groups of slow-moving aircrafts in attack on German ships in the early stages of the war, which were noticeably inferior in combat qualities to, for example, Japanese and American aircrafts. In addition, the Germans did not have the problem that became the main one in the war in the Pacific Ocean, repelling attacks by dive bombers. The enemy simply did not have such aircrafts, and the skill of British naval aviation pilot was not comparable to the Germans, Japanese and Americans. 16 37mm machine guns, installed in twin mounts, 2 on the sides of the Bruno turret, 2 on the bow superstructure, and 4 around the stern fire control posts, were not fully automated, but having a rate of fire up to 80 rounds per minute, and theoretically up to 160, were the main means of close air defense on all large German ships. The ammunition supply usually amounted to 32,000 unitary rounds for all mounts. According to the design, the ships carried 8 20mm machine guns on single mounts with manual service, 2 on the spar deck on the sides of the Bruno turret, 2 on the upper platform of the bow superstructure, 2 on the funnel platform, and 2 on the quarterdeck. With the beginning of the war, 2 more barrels were added on the upper deck in the stern. These machine guns had a practical rate of fire of 120 rounds per minute and theoretical 280. A freely swinging barrel, the vertical plane from -11 degrees to +85 degrees, and fired cartridges of 20 rounds. During the war, the number of 20mm machine guns on these ships was constantly increasing, and most of them appeared on board during their stay in Brest. Scharnhorst received 18 additional barrels, Gneisenau 14. Machine guns of the new model in single barrel or 4-barrel mounts were placed where there was free space, on the roofs of the towers, special platforms, on the open deck, or in place of some of the searchlights. The maximum number, 38, was carried by Scharnhorst in 1943. During the modernization of the Gneisenau, the number of 20mm machine guns was planned to be increased to 6 4-barrel and 8 single-barrel mounts. The barrel of the new machine gun turned out to be slightly lighter, and the practical rate of fire increased to 220 rounds per minute, theoretically even up to 480. The ammunition supply, which was 20,000 rounds at the beginning of the war, subsequently grew proportional to the increase in the numbers of machine guns. The original design did not include torpedo armament, but after returning from cruising in the Atlantic at the end of March 1941, Admiral Lutyens, who commanded this operation, proposed installing deck torpedo tubes on both battle cruisers. In his opinion, sinking transports with artillery fire required a lot of time and shells, while torpedoes, especially at close range, could do this faster. The High Command of the fleet agreed and ordered that while the ships were in Brest, 2 triple-tube 433mm tubes removed from the light cruiser Leipzig be installed on Gneisenau and from Nuremberg on Scharnhorst. There was no torpedo firing control system other than sights on the tubes themselves, and servicing was the responsibility of the entire aircraft machinery gun crews. The torpedoes, of which the ships took 14 pieces, were stored in boxes located next to the tubes. The tubes had no protection and could easily be disabled by even small caliber shells, shrapnel, or a blast wave. In the last Battle of Scharnhorst, one of its torpedo tubes was disabled by a nearby shell explosion. Since the German fleet had no aircraft carriers, large ships were forced to carry seaplanes for reconnaissance, fire adjustment, and even some offensive actions against enemy ships. Air bombs were stored in a special cellar. The hangar arrangement on these ships differed from each other. On Scharnhorst, the larger hangar was extended by another 8 meters during a major overhaul in 1939 to accommodate 3 Arado 196 planes. The hangar roof was sliding. 2 cranes were used to remove the planes from the hangar and place them on the catapult in its stern. Another plane could be stored on the roof of the Caesar turret. Initially, the turret had a catapult, but it was removed from both ships during the winter overhaul of 1939. Both ships made heavy use of their onboard aircraft throughout their careers, but especially during the Atlantic campaign in early 1941. However, having aircraft on board exposed the ships to additional risk due to the need to store highly flammable aviation fuel. During the Battle of the North Cape, Scharnhorst took several hits to her hangar, causing large fires. To control fire at surface targets, these ships received a set of instruments of the 1935 model, which was also equipped on battleships of the Bismarck class and heavy cruisers of the Admiral Hipper class. This complex controlled the fire of guns of both the main and the secondary guns. It consisted of 3 directors and rotating turrets, on the bow superstructure behind the mainmast, equipped with 10.5 meter stereo rangefinders, and on the conning tower with 6 meter stereo rangefinders. 3 turret rangefinders with a base of 10.5 meters, and bow and stern transmitting stations with computing devices for both calibers. The rangefinder was removed from the entrance turret in 1941, and the openings were covered with armor plates, since its lenses were constantly flooded with water and splashes. The artillery fire control posts were located in the director turrets. They were equipped with telescopes for the artillery officer, as well as for horizontal and vertical gunners. The director turrets were stabilized in 2 planes by gyroscopes, central related to the ship's course and local ones along the horizon. The telescopes were stabilized by tracking systems with output electric engines, and any resulting misalignments were compensated by vertical and horizontal gunners. The geometric computers received the target bearing, the course of the ship, its speed, and the range to the target as an input values. The target speed, its inclination related to the side axis, course, and range at the average of the reading of the main and turret rangefinders or according to radar data were the output values. The ballistic computer received the value of the speed of change of the distance and bearing, and taking into account the weather, the initial velocity of the projectile, its rotation, air humidity and wind, issued the full angles of the vertical and horizontal aiming. Each block of computing devices had 2 spherical angular converters, allowing for the roll and pitching. The main artillery fire control system allowed using from 1 to all 3 turrets on one target, or firing at 2 targets simultaneously. Only the vertical devices had power remote control, and the horizontal drives were controlled manually according to the tracking the pointer principle. The same principle was used in the vertical drives if the remote control was turned off. If the ship's movement in space were too abrupt for tracking, a time interval compensation device was used. In this case, the vertical and horizontal angles were produced at an arbitrary speed, but upon passing the required bearing value of the angles, the firing circuit was automatically turned on. The medium guns fired a solo shot with a lead of 10 to 20 milliseconds, so that the projectiles would not interfere with each other in flight, and the dispersion would be as small as possible. The firing delay after the circuit contacts were turned on was quite large. The standard German electromagnetically controlled striker would fire in about 150 milliseconds. The fire of the 105 mm anti-aircraft guns was controlled by a 1933 type system. 4 directors with 4 meter rangefinders were located in spherical turrets on the sides of the bow superstructure and pipe. 3-axis stabilization was provided by gyroscopes without servo motors. The directors had good protection, but weighed over 40 tons. The gyroscope rotor alone weighed 260 kilograms. The entire aircraft guns were serviced by portable rangefinders with a base of 1.25 meters. They did not have a central fire control system. The Germans considered it more important to simultaneously fire at as many targets as possible. To eliminate targets at night, the ships had 5 1.5 meter wide searchlights, one on the bridge of the forward superstructure, 2 on the platform around the funnel, and 2 on the main mast platform. Searchlight control posts were located in the forward superstructure and in the stern. The German Navy was one of the first to correctly assess the capabilities of radar target range determination. The Germans began work on a shipborne radar in the summer of 1933, and in October 1934, a prototype with a range of only 12 kilometers was installed on the yacht grill. Successful tests in 1935 of the radar equipment developed by Dr. Wilhelm Runge, operating on 50 cm waves, allowed the German Navy in February 1936 to conclude a contract with the Gemma company, which soon developed an 80 cm radar capable of detecting a moving ship from a distance of 35 kilometers and a flying aircraft from 48 kilometers. The radar was tested in Swinemünde, considering its use not only in the Navy but also in the Army. The naval version was codenamed Seetakt and the land version Freya. The first warship to receive the Seetakt radar was the cruiser Königsberg, while the battle cruisers Admiral Graf Spee, Admiral Scheer and Deutschland received more advanced models. According to other sources, the world's first naval radar appeared on the Admiral Graf Spee in 1936. With the outbreak of war, Scharnhorst and Gneisenau received 2 Seetakt Fu-MO-22 radar installations each, one on the bow director, located on top of the bow superstructure, the other on the stern. The detection range of a large ship was 25 kilometers, the bearing accuracy was 5 degrees. The bow installation had a circular sector of action, but from the stern angles it was obstructed by the superstructure. Therefore, a stern radar was installed, similar in design to the Freya aviation radar. The Fu-MO-22 model, being sensitive to humidity and shaking from gunfire, did not fully satisfy the Navy requirements. Therefore, during the war more advanced models appeared, the power of which exceeded 15 kilowatts, the range error was reduced to 50 meters or less. Gneisenau in January 1941 and Scharnhorst in early 1942 received new model radars, which allowed a bearing error of only 0.25 to 0.3 degrees and a range error of 70 meters. In 1943, Scharnhorst received additional radars. The Germans, however, stopped work on radars with a wavelength of a few centimeters. The responsibility for this decision fell on many officials, but Hermann Goering played the main role. He failed to properly direct the efforts of the electronics industry, although if he had been shown how a radar with a wavelength of several centimeters worked, he might have taken steps to complete the work on it. The mistaken decision to stop work on centimeter radar for the Navy belongs to Admiral Witzel, who had a strong influence on the liaison officer between the Naval High Command and the Gemma Company. As a result, Germany, which was ahead of everyone in the technical aspects of radar at the beginning of the war, found itself behind Britain by mid-1941. The Scharnhorst-class ships were designed in an era of excessive enthusiasm for speed, and therefore had high-power mechanisms. Like their predecessors, the Deutschland-class armored ships, they followed the principle of being faster than a stronger opponent and stronger than a faster one. German engineers spent a lot of time and effort to create truly successful diesel engines for their armored ships. Diesel engines provided low fuel consumption and a huge cruising range, allowing them to remain at sea for a long time without refueling. But this advantage could not be realized on a ship with a speed of 30 knots and limited space for a power plant. Developing diesel engines for such a high speed would have delayed the construction of the ships for a long time. The only alternative was a steam turbine plant, since the shipbuilding department objected to the use of a combination of diesel engines and turbogear units. At that time, turbine plants with high steam pressure and temperature were successfully used on the new liners of the East Asian Express Company. For several years, coastal power plants had been successfully operating, where generators used steam with high parameters. All this, in principle, did not promise difficulties when using similar plants on warships. However, naval engineer mechanics, despite all the advantages of such plants, pointed out the danger of their maintenance. Only comprehensive testing could dot all the I's and cross all the T's, but there was no time to conduct them. Admiral Raeder personally intervened in this matter and decided to take a risk, ordering installations with high steam parameters to be installed on the new ships. The steam parameters on these ships, pressure of 58 atmospheres and temperature of 450 Celsius, were much higher than on all their contemporaries, with the exception of Bismarck and Tirpitz. The steam was generated by 12 3-collector boilers with a superheater and economizer, and 3 turbo units developed a capacity of 125,000 horsepower, or for a short period of time when forced, 160,000 horsepower. The entire power plant on these ships turned out to be lighter and more compact than a diesel of equal power. However, fuel consumption was higher and a large reserve was required for the same cruising range. Displacement restrictions and the priority of armor protection forced the abandonment of a long cruising range. But both the remaining fuel reserves and the high speed of its use created stability problems. Since the Germans did not like to compensate for fuel consumption in tanks with salty seawater, not counting the side tanks, some other solutions had to be found. It was decided to place the side fuel tanks as high as possible, so that the stability of the ship would increase as the fuel was consumed. The oil-water separator, which first appeared on Admiral Scheer and allowed water ballast to be taken into the fuel tanks, was used on all German ships. To increase the cruising range, the outer and inner side ballast tanks were filled, at least partially, with fuel. But the lower bow fuel tanks were initially left empty to eliminate the inherent trim by the bow. The stability of the ships did not always improve with fuel consumption, so at times it was necessary to use outboard ballast. During trials, Scharnhorst developed 31.65 knots and Gneisenau 30.7 knots. The cruising range at 19 knots, with a fuel reserve of 61 and 5,300 tons respectively, turned out to be 71 and 6,200 miles instead of the design 8,200. At 15 knots, 9,000 miles, and at the specified full speed, 22 and 2,900 miles respectively. The sometimes cited cruising range at 19 knots of 8,400 miles for Gneisenau and even 10,000 miles for Scharnhorst seems greatly exaggerated. As a result of the significant expansion of electrical use, particularly in the weapons systems, each ship received generators with a total capacity of 4,500 kilowatts, including 900 kilowatts of diesel-powered backup in case of battle damage. Scharnhorst and Gneisenau were the first capital ships of the reviving German fleet, and their design was marked by numerous limitations. The Germans decided to build these ships despite the possible shortage of steel and equipment. They took a risk, and both ships entered service at the very beginning of World War II. The intense activity and numerous damages received provided an excellent opportunity to assess their strengths and weaknesses. Their main drawback, caused by political rather than technical reasons, was the small for a battleship 283mm main caliber, much to the disappointment of Gross Admiral Raeder. It was the lack of guns on Scharnhorst, whose shells could penetrate the armor of 35,000-ton battleship, that became the decisive factor in its demise. If these ships had been rearmed with 380mm guns, sacrificing the commissioning time, their combat effectiveness would have been much higher. But even the 283mm guns turned out to be quite good in the conditions for which they were designed. For their size and displacement, they had powerful protection, although they lacked the thicker upper citadel of Bismarck. The 350mm bell did not go well with the 283mm guns, violating the principle of matching the protection to the main caliber adopted by all other battleships. The main weaknesses of Scharnhorst and Gneisenau were the weak deck armor and the thin upper belt, which allowed large shells with a flat trajectory to penetrate the lower armor deck. However, the combination of side armor, sloped armor deck, and torpedo bulkhead provided excellent protection for vital parts in close combat. The weakness of the deck armor was revealed during the bombing of Scharnhorst at La Palisse and Gneisenau at Kiel. The 356mm shell hit on Scharnhorst's boiler room in her last battle demonstrated the need for a thicker upper belt to provide additional protection for the lower armored deck. Ships of this type also had insufficient protection against torpedoes, especially in the area of the main caliber turrets. This was caused by the desire to achieve high speed by sharpening the hull lines and by displacement limitation. The design of the torpedo protection structure also turned out to be erroneous, which was demonstrated by the explosions of torpedoes with a charge of 204 kg and 340 kg. The main drawback was that the torpedo bulkhead ended abruptly on the lower armor deck, and its welded joints were not of high quality everywhere. Weight problems did not allow the torpedo bulkhead to be extended to the upper armor deck, which would have provided better structural integrity, more reliable fastening of the torpedo bulkhead, and a greater ability for it to deform without destruction. The German designers knew about this drawback when they developed the project. Even more obvious was the weakness of the torpedo protection at the end of the armored citadel, where according to the design, the protection had to withstand the explosion of 200 kg of TNT and not 250 kg as in the middle part. There was a serious drawback in the torpedo protection in the area where the propeller shafts passed through the torpedo bulkhead. When torpedoes hit this place, the shafts received serious damage, and the gases, formed during the explosion, did not meet sufficient resistance from the structural elements on their way. The medium caliber artillery was quite adequate for the nature of the expected battles, but the clashes during the war years refuted the pre-war views of the Germans. The combination of lightly protected deck 150mm mounts with armored twin-gun turrets turned out to be unsuccessful, although the Germans understood this even before the ships were commissioned. Deck mounts quickly failed even in combat with cruisers. It would have been better to install 2 twin turrets instead of 4 single mounts. The 150mm turret guns should have been adapted for anti-aircraft fire, as the French did on the Richelieu-class battleships. Such rearmament could have been done before the war. The firing range of the 105mm anti-aircraft guns was not enough to shoot down or drive away aircrafts before they dropped torpedoes or bombs. The slow British swordfish and the imperfect British bombing and torpedo dropping tactics did not allow the inadequacy of the 105mm guns to modern combat to be noticed in time. But when operating in the Pacific Ocean, in battles with faster and more technically advanced aircrafts, the weakness of the air defense of the German light ships would have been immediately revealed. Both times, when these ships were subjected to massive air raids, they were covered by powerful fighter forces, leaving the anti-aircraft guns only a supporting role. Mine damage showed that auxiliary machinery, electronics, artillery, electrical equipment, and the foundations on which they were attached were improperly designed and could not withstand impact loads. Auxiliary machinery in the engine and boiler rooms failed even in the event of a non-contact explosion, which resulted in minor hull damage and flooding. The Germans had used high-steam power plants too early, despite the objections of the Naval Construction Department. Equipping several classes of warships with boilers of different design at the same time led to numerous delays and increased maintenance costs, not to mention the frequent outage of ships for long periods due to various boiler malfunctions. It's enough to say only about the superheater tubes. The situation was even worse with the auxiliary equipment and fitting for the boilers, which failed even more often and took even longer to repair. In addition, the use of a turbine plant instead of a diesel plant severely reduced the cruising range. The design of the Scharnhorst-class ships can be considered satisfactory only in view of the limitations that the designers had to face. The ships were well protected and armed for their size, given the short ranges of the North Sea battles. The main caliber, however, was too weak for a capital ship of World War II. The anti-torpedo protection did not live up to expectations, mainly due to contradictions in the hull structure. The horizontal armor in the area of the machinery was very weak, and the lack of the thick upper citadel allowed heavy shells to penetrate the boiler room, which is what happened in the last Battle of Scharnhorst. The speed was excellent, although precisely because of this, it was not possible to give the ships the same protection as the German battle cruisers of Great War. However, the last Battle of Scharnhorst against superior British forces demonstrated the high quality of its design and construction. She fought for more than 3 hours until its main battery spent its ammunition, having sustained heavy damage. It took about 11 torpedo hits to sink it. The lack of an escort prevented it from repelling the attacks of the British destroyers, and after receiving several torpedoes, Scharnhorst was overtaken by a stronger enemy and forced into an equal artillery battle. The German destroyers were also able to attack the British battleship Duke of York, causing damage to it or reducing the effectiveness of its guns. Their radars, with the bow radar of Scharnhorst out of action, could have detected the British force in time, and the Germans would have had time to escape. The Luftwaffe detected the British ships, but when the information reached Scharnhorst, it was so distorted that it led to an erroneous interpretation. The outcome of the battle was decided by a 356mm shell that hit boiler room number 1, and Scharnhorst, having lost its speed advantage, allowed the British ships to close to pistol distance and carry out the inevitable torpedo attacks. The loss of Gneisenau was caused by a calculated risk. Contrary to instructions, the ship, which was in dry dock before leaving for Norway, was fully loaded with ammunition. The only dry dock available at that time in Kiel was located next to the pier where Scharnhorst was being repaired. This situation, with 2 large ships close to each other, was hotly debated by the naval leadership. The proposal to remove Scharnhorst was rejected, as they did not want to interrupt the repair works. The proposal to unload the ammunition from Gneisenau was also rejected, as this would have kept the ship in the dock for 4 days more, preventing it from getting through to Norway during the new moon. The shipyard asked the High Command of the Navy for instructions, and Raeder ordered Gneisenau to be docked with ammunition. But Raeder cannot be held entirely responsible, as Hitler had severely criticized him for keeping the ships in the docks, insisting that they to be transferred as soon as possible to Norway, where they were to operate against convoys to Soviet Union. Scharnhorst and Gneisenau, the first new large ships of the Kriegsmarine, during their combat career constantly demonstrated the significant successes of German military shipbuilders, who managed to create ships with good protection and speed, albeit with weakened armament, within the limits of limited displacement. In fact, these were the last battlecruisers in the world in the form in which they were traditionally imagined by the German fleet. The desire to have similar ships prompted the leadership of USA, Japan, Netherlands and especially USSR to sanction work on their creations. These followers of Scharnhorst were distinguished by higher speed, sometimes more powerful armament, but incomparably worse protection, which made them obsolete even before they were laid down. After all, the main trump card of the Germans was precisely protection, which was clearly confirmed by the last Battle of Scharnhorst. Shot almost point blank by heavy 356mm shells, she went to the bottom only after 11 torpedoes from British destroyers and cruisers hit her. For comparison, it can be recalled that the giant Japanese Yamato, twice as large as displacement, perished after receiving the same number of aircraft torpedoes, which also had a smaller killing force. And the conditions in which the crews of the ships had to fight and struggle for survivability cannot even be compared. A lone rider in a stormy December Norwegian Sea on a polar night, and a giant sailing as part of a unit in the almost calm April waters of the Pacific Ocean. In next video, we're gonna talk about Scharnhorst service history.